Now, let's look at a detailed forecast regarding how you can use different time series forecasting mechanisms to predict the future value of, let's say, a stock price or index, or for that matter, anything that involves time as a factor. So, for that, I'll take a simple example. Let's say I'm considering the Sensex. I have the data right from Jan 2006 up to February 2015, and I have the Sensex values across this period. Now, let's say I want to predict the value for March 2015. What are the various avenues that are there with me? The first thing, I'll see if there is any kind of a trend in the process. Now, how do I check out for the trend? I'll create a time variable 1, 2, so on. Right? I'll create a time variable like this. And I'll simply do the regression by taking Sensex as the dependent variable and time as the independent variable. So let me do that. I'll go to the data analysis, wherein I'm taking the regression by looking at the Sensex as the dependent variable and the time as the independent variable. And of course, I'm selecting the label out here. All right, when I'm running this regression, this is what the output of the regression coming out to. The R squared is around 64%, which means the variation in the values of the Sensex contributed by this time as an independent variable, explained by time as an independent variable, is around 64%. Mean the time variable is not able to explain the remaining 36% of the variation, right? All right, so this kind of a model is our linear trend model. I'm looking at a linear regression here. Whereas I could even try out a quadratic trend kind of a model, right? In a quadratic trend, I would also look out for a time squared, right? I'll take out this time squared. This time I'll try out the regression using these two as the dependent variable, independent variables, and this as the dependent variable, and see if there is much improvisation in the estimate by any chance. So here, instead of taking only this as the independent variable, I'll select these two columns as the independent variable. Now this is resulting in an R squared slightly better, 69% is being contributed, and the adjusted R squared is 68.6 as against 64 here. So probably a quadratic trend looks much better compared to a linear trend. And even when you look at the standard error, it's working out to 2513 versus 2680 out here. So because there is even a reduction in the standard error, it looks like it's better for me to proceed with this kind of a model, wherein my model will be the price at that point T is nothing but 1.058 T squared minus 4.1673 T plus 13,233.25. So this is the kind of a model or a formula we are using to predict the price using this quadratic trend model, which is resulting in a standard error of still at the range of around 2513. Now, one more way out for me is, instead of depending more and more on either the linear trend or a quadratic trend, I can even try out some kind of exponential or log linear kind of a trend model. So when I'm talking about log linear trend, we are purely looking at taking the logarithm of the Sensex. Right, instead of taking the Sensex as it is, I'm looking at the logarithm of the Sensex. So I'm taking this value, right? And now I'm going to see, by taking this as the dependent variable and this as the independent variable, is there any kind of an expression, which means here my model is log Sensex is equal to a plus bx. Now this is where I can very well look at Sensex is nothing but e to the power of a plus bx. So such kind of a model is called as a log linear trend kind of a model. We have to see if the r squared is improved either through this model at all. So we'll go to this regression again. This time consider this as my dependent variable, and I'll consider only the time variable as an independent in this case. Check out, the r squared is just around 62. So at least in this case, the r squared through this model is much lesser compared to the earlier two models. So probably it's as good as I'm relying more on the quadratic trend model for the prediction rather than the linear or the log linear trend model. So this is where I'll look at the trend part of it. So what I'll do is, now that we have tried all these things, I will basically go for finding out the predicted value based on purely the trend part, right? Which means I'll use my quadratic trend model to typically do the prediction of the index. Now, what is my quadratic trend model? Yes, intercept plus this time variable multiplied by whatever is the coefficient of time plus the time squared coefficient. I multiply it by the time squared here. Overall saying, as per this model, this is what is my predicted price across. So during different periods, these are the predicted values of the Sensex that are coming out. So this is what has been predicted by my quadratic trend model. I'm not depending on the other trends here. I'm going purely with the quadratic trend. Now, based on this, I will look out for my error. The error is simply coming out as the actual minus the predicted. Okay, the error is coming out actual minus predicted. In some cases, there is some amount of negative. After that, a few periods where there is a continuous positive. Again, a few periods of negative, positive. So this is how the error has been changing. And here, my major intention is to check out, is there any kind of seasonality? But of course, again, a practical experience will tell me that majorly with the stock prices and indexes, we are hardly seeing any kind of seasonality in the data. So which means I really don't need to bother much about the seasonality. Now, which means, do I say that this much of randomness on an average is present in my forecast and leave it off? Now, this is where the traditional, the ARIMA based models are coming into picture, which talk about auto regression, integrated, and a moving average. When I say auto regression, I'm trying to see whether these error terms, they are internally correlated and can they be having some amount of regression among themselves. Right? I really want to see whether they are correlated by any chance. Now, if I really want to check out the level of correlation between them, I can very well see a simple correlation between these error terms, probably up to 1 period lag I will see, right? These error terms with 1 period lag. I'll start with from the next one and I'll go to the last. I'm seeing if there is any correlation between the error terms. Looks like a very strong correlation, 0.90. So this is giving me a good hint that the error terms, they have a very strong correlation with each other, which is a clear indication that some kind of auto regression can be present, or we can try to predict. Right now, let me call this error for the sake of calling the error, I'll call it as my updated data. Right, though both are the same, just for our understanding, now I'll take this to be my updated data. I get a correlation of 0.90, which means the next period is very much dependent on the previous period. So 1 period lag correlation is 0.9. Even if I look at 2 period lag correlation, I can see probably when I am looking at 2 period lag, I'll take the correlation between this up to 2 periods before, and from here I'll take it up to 2 periods before here. So 2 period lag is also 0.8, very strong, right? Even if I look at 3 period lag, it looks like the correlation across the time is very strong. I'll take 3 periods before here, and also I'll take 3 periods before here. Looks like again 0.71. So looks like it's a fading, but there is some amount of stronger correlation across the period. Now this is what will give me a kind of a pointer to finally think of a kind of auto regression kind of a function, where I'll consider this as a dependent variable and even this as an independent variable and try to arrive at a predicted value. So when I'm taking the dependent variable as the current variable and independent variable as 1 period old variable, lagged variable, and run a regression getting a plus bx form, which means yt equal to a plus b yt minus 1 kind of a form. This kind of a model is called as an auto regression model of period 1, because I am considering only 1 period lag. But if I am taking an independent variables as both 1 period old value as well as 2 period old values, we call that model as an AR2 model, auto regressive model of order 2. Now let's try out how I'll take some, first let's build AR1 model. I'll take some A, I'll take some B. Right, let's go ahead with taking some A as 10,000 and B as some 1. And using that, I want to create a predicted value here. Right, the predicted data. So from this period onwards, what I'll do is A, right, yt is now if I assume that this is what is my yt's. Right, now here what is that I am trying to do? A plus b times yt minus 1. This is what I am giving it as a predicted using the AR1 model. Right, so I mean I've just dumbly assumed some 10,001 here. We'll try to optimize them using a solver at a later point. So when I do this, these are my predicted data. Here the data means error, which will adjust it back to our original. So this becomes my predicted data using the AR1 model. Based on that, I'll try to find out my error squared using the AR1 model. The error squared is nothing but whatever was my actual minus the predicted, take the square. The error squared coming out to be this, and based on that I can find out my average error. Average error is the summation of all these error squares, and I will call something as root mean squared error, RMSE, which is the square root of this number. Okay, so this is my root mean squared error, and my intention is minimize this by changing these two. Let the system change these two variables and finally arrive at this value to be the minimum. So this is where I rely on solver, right? I will select that this value needs to be minimized by changing these two values, and this is where I'll try to see when I solve this. Yes, I'm getting some kind of a value where my RMSE is coming out to 11,100. Let's try it again. Okay, here let me put a higher number of iterations. Okay, here the average error, I have taken the sum. Actually, I have to take the average. Okay, let me take the average of it. Right, let me take not the sum. Let me take the average. So the root mean squared error has come out to 1063. Right, which means instead of having an error of 2513 here, now my error in the prediction has come down to 1063. I have improved as a part of my prediction model. And even if I look at instead of error squared, let me take even the error, which is actual minus the predicted. So this is what are the errors in each of the periods. Now what I can very well do is I can find out the error for the next period. Now I can use this model to find out what could be the error for the next period, and I can do the adjustment also. So if you look at for the next period wherein I am looking at this particular stuff, so I can very well look at the number for the next period. Next period has come out with 3,364. So what am I going to do to whatever the prediction that has come out through this mechanism? So what is the prediction that is coming out through this particular mechanism? If I had gone only with the quadratic trend, which is the F column, let's say for March 15, right? Let's say for March 15, my prediction, this I'll take as 111. So based on this, my predicted value is going to come out to, what are these D's and E's here? Times squared also I have to consider. So even let me consider this. So my predicted, if I go purely with quadratic trend alone, it is 25,806. And now when I'm going with the error prediction, it's even this one that is coming up, which means as per our model, if I add these two things, the predicted value for the next period is going to be somewhere around 29,171.8. So this is what is the prediction that the AR1 model is going to give to me. Autoregressive of the order 1. The error has typically come out to the extent of only 1063, means our prediction has improved drastically. The same logic now I can continue testing out if AR2 model is appropriate for this data or not. Now how do I go about with that? In AR2, the equation what we'll have is yt equal to a plus b yt minus 1 plus c yt minus 2. So building the same stuff here, let me start with a as some 60. Now that we got some values there, b I'll start off with some 0.9 and c also let me start with 0.9. Now based on this, I'll get the predicted using the AR2 model, right? I'll simply take, so because I need AR2, I'll start from here. A plus B times T minus 1, YT minus 1. This is YT minus 1 plus C times YT minus 2. So this is giving me my AR2, the predicted values. These become my predicted values. Based on this, I can find out the error in the prediction, wherein I'm going to take the actual values minus the predicted values, right? I'm taking the error. These are my errors. Now I'm taking my error squared, wherein I am taking the squared of this, right? The error square is being considered, and from here I am finding out what is my average error, wherein I am taking the average of all these resulting in this much. I'll find out RMSE, which becomes the square root of this average error, resulting in 2531. Now my intention again is to minimize this by changing these three. So I'll get into solver again with an intention to minimize this by changing these three. And once I solve this, oh yes, here I am getting into an RMSE of 1107, which is higher than this, which means I am not able to improvise the situation better using the AR2. So AR1 model is much better for me compared to AR2 model. So from the auto regression perspective, I'll stop this model. I'll simply go with AR1 model, whatever the error that I am predicting for this particular. Now I can actually delete these things. So let me check out here now. Yes, 1068 still. The error is around 1068. The RMSE is around 1068, which is higher. So which means I may not rely more on the 2-period stuff. So only 1 period lag. So AR1 is the model which I am relying on. Now I can move on to the next part, which is the moving average. So in moving average, what happens is I'll build a model like this: YT A plus B times YT minus 1. This is up to here, it's AR. But in C, what I'll take is, I'll take the prediction error, which is the actual yt minus 1 minus the predicted yt minus 1. This is what I take as a C value. And probably if I am doing the same learning from all the previous, I take actual yt minus 2 minus the predicted yt minus 2 as a part of my, these go as a part of the moving averages. Different weights to each of these is going as a part of the different moving average models. So from here, if I am looking at, let's say in this case, I'll try to build that, right? So A, B, C. So what I'm saying is predicted going with AR1 MA1 model. I'm integrating these two things, right? So for this, what is that I require? First, let me assume some numbers. Let me assume a 60 here. Let me assume a 0.9 here. Let me assume some 1 here. Based on this, I am creating, right from here I can create, I suppose. So what we'll do is A plus B times yt minus 1. Yt minus 1 is this one, plus C times C is this one. The learning, I mean whatever was the predicted value minus the actual. So this is the actual minus whatever was the predicted here. So this is what we will consider as the predicted value of AR1 MA1 model, right? And because we don't have any predicted value here for a very old data, we can make a simple assumption that the predicted is same as that of the actuals. So when I make it, all these predicteds came out like this. So from here, I can again find out my error squared. Probably I'll start from the second one because the first one is predicted and actuals. We have taken it exactly the same. So in the second one, I'll take the actual minus the predicted whole squared. This comes out to be our error squared. And from here, I can find out the average error, which comes out to be the average of these numbers. And from here, I'll try out root mean squared error, which comes out to be the square root of this. My intention again is to minimize this using solver. Minimize this by changing these three things. And even in this, okay, I think we might have got some additional, yeah, we have got something additional here. So let me take that out and see here the error is coming out to 1063 again. 0.2 and 0.82 slightly on the higher side here, but otherwise this model is simply saying 28 plus 0.87, either this or this, both of them are giving more or less similar levels of RMSE, so I can rely on this model or on this, but going with strictly on the lowest error, I see this model more applicable compared to this. But even if I am going with this model, my predicted value of the error for the next period is going to be 3226. So whatever the prediction that came out through the quadratic trend model, I'm simply adding up this 3226 and giving a prediction for the next period. And obviously in this entire prediction, the error that is there is to the extent of 1063. So this is the way we typically go forward in terms of doing the auto regression, and probably here I can try out MA2, MA3. So you can very well go further with an intention to where exactly your root mean squared error is coming to be the minimum most possible. So wherever you are getting that to be the minimum most possible, that is the one you are choosing for your prediction purpose. All right. And if you are doing that same, this entire exercise, if we are doing with the original data like this, we get the models as AR and MA, probably depending on how many periods of AR we have used and how many periods of MA we have used. We call them as ARMA 1.1 model, or when I say I'm using ARMA 2.1, it means I'm using AR2 model combined with an MA1 model, right? So that's how the naming comes out. But in some cases, instead of doing it on the original data, we may wish to do this entire analysis on the differences of the original data. Right? When I'm saying the differences of the original data, so I'll not take the data as it is. I'll take the differences of the data. So which means I will be taking this value minus the previous value. This is what I'm calling as the difference. So if I do this entire exercise, not on the original data, but on the differences, which means I'm going to predict the differences rather than the originals, that is where I call my model as I, where in the ARIMA, I is coming into picture when I am working out on the differences rather than on the original. The same process. Now you assume this as the data and then again do AR model on it. You again do MA model on it. But because we are taking the difference and we are doing on it, we call these kind of models as ARIMA model. But at least if you are comfortable in terms of doing the prediction better with respect to ARMA, AR and MA models, that really helps us in terms of doing lots of forecasts with much more accuracy built into them. All right.